Let's look at section 1.3. This section has a lot of pre-calculus material in it. So the notes may feel a little long, but we're going to go nice and slowly so that you can make sure that you fully understand these new concepts. So the first thing we have are talking about continuity. So what continuity means is either that we are continuous or discontinuous. A graph is continuous if there are no breaks, no holes, or no gaps. So we can see on the right-hand side here, this red curve, right, that graph, I never have to pick my pencil up. It's the arrows indicate that I go on forever, and then also I never have any holes or gaps. If I was to trace, I never am going to pick up my pencil. So we are continuous, okay? Now, a discontinuous graph means the opposite, right? It means that there isn't that sort of solid flow from start to finish. We have a break, we have a gap, or there is a hole. Now, there's 3 different scenarios here that you need to make sure you have understood. And the first one is that we could have removable discontinuity. Okay, so removable discontinuity is when there is a hole. Okay, so we have a line that is going on and on and on, and then all of a sudden there's a little open circle, there's a hole, but then it picks right back up and continues on. So if there's a hole at 2, we're plotted everywhere up through 2, 1.9999999, and then same thing, 2.000001, but there would be a hole that exists. That's called removable discontinuity. Okay, our jump discontinuity is the next one to know, and that's when we have a break in the graph, okay? So, or a jump. This is like what you may remember as a piecewise function. So we're continuous for a while, and then all of a sudden it stops, but it picks right back up, but at a different location now, and then we continue on. So that's jump discontinuity. And the last thing we have is infinite discontinuity. And that's usually when we have a little gap in between 2 spots. That infinite discontinuity is when graphs are approaching both infinity and positive infinity, though. Okay, so those are our 3 scenarios. Make sure you have the circled parts understood. Removable, jump, and infinite. And think about what those pictures look like. Now, let's talk about what a limit is. Okay, so a limit is a unique value that a function approaches but never actually reaches. Are there limits for every function? Absolutely not. But often we have a limit. And so what that limit is saying is that as I come from like the left of a graph and the right of a graph, we approach some number, but maybe it doesn't actually exist. Maybe there's a hole there. So maybe we're approaching the value of 10, but we never quite get there. We get to 9.99999, or we get to 10.00001, but we never actually get to 10. So therefore, my limit would be 10. So let's look at one of these examples together. A notation that we see, just so you're familiar with limit notation, is this LIM for limit. And then with this little arrow with the X here, that's what the limit is approaching. Okay, so that's what we're going to be seeing is as I approach 5, what's the limit? As I approach 10, what's the limit? As I approach infinity, what's the limit? And that'll make more sense as we go. So this first example we have here is we're given an equation. Okay, it's a fraction here. And we want to know what the limit is as I approach 2. So you can do this in a couple of ways. If you have a graphing calculator, a table is fantastic. If you don't have a graphing calculator, that's okay. We can make our own table. And what we want to do is when we plug in a 2 here, we're going to get an undefined statement because there's going to be a 2 in the denominator and that is so the 2 in the denominator gives a 0, and that's no good, okay? So for example, and I just want to show you that real quick, right? If I was to plug in a 2 in for this, we would have 2 minus 2 all over 4, right? 2 squared plus 2 minus 6, and that would give me a 0 in the bottom, which is undefined. So that's why the 2 is not actually defined, but we're going to try to figure out what does this graph actually approach there, okay? So what we're going to do is we're going to make a table of points that are really close to 2, because a limit, again, is what number are we approaching as we come from the left, so as we approach 2 from the left, and then as we approach 2 from the right, what is happening? So you don't always need to stick with the values that I've made in this chart. Okay, you could test 1.8, 1.9, 1.95, but here are a variety of ones that we can test. Now, when I plug those values into my calculator, okay, we can just do them each individually if you don't actually have a table for your graphing calculator. So I would plug in 1.9 into the equation, and when we do that, we get 0.204. Then I would plug 1.99 in for x, and when we do that, I get 0.2004. And when I plug in 1.999, I get 0.20004. And now let's do the same thing. Let's approach the values a little on the right-hand side of 2. So that would be a little past 2. At 2.001, I get 0.19996. At 2.01, I get 0.1996. And then at 2.1, I get 0.19607. So let's analyze this. Do you see a number that these are all approaching? For instance, look at all those blue values. Are they all close to 5? Are they all close to 0? Are they all close to -17? What are they approaching? And so right here would be where 2 is. So as I approach 2, we can see that the limit is approaching 0.2. Okay, so the limit is going to equal 0.2. If all those values from my table were close to 0.5, then my limit would be 0.5. If they are all close to 7, then the limit would be 7. Okay, so when you're evaluating limits, it means that it's probably undefined at that point, but we can look at values to the left or to the values of the right to see what we are actually approaching. So you try this next example here. Here's my function, x minus 5 over x squared minus 3x minus 10, and we're going to find the limit as we approach 5. So you can set up a chart, okay? And if you have a graphing calculator, you can use similar values to like the chart that is above. Or if you don't have a graphing calculator, you don't need to be as specific like that. We could do things like 4. We could do 4.5, and we could do 4.9. Then we would have that break because we're looking at where 5 is, and then we could test, for instance, 5.1, 5.5, and 6. And that should give you a solid enough approximation. If you want to be more specific, you can also be more specific, okay? We could simply do 4.9, 4.99, and 4.9999, like the chart above. And then we could do 5.001, 5.01, and 5.1. As long as we are picking values close to the 5 that we're evaluating, your table should give you enough information of what the limit we are approaching is. So try that out. Remember, if you don't have the graphing calculator table function, you're just going to actually plug those values into the function to get your y values. Let's continue with limits. This time around, the next three are as x approaches infinity. Now this time, you don't necessarily need a calculator for it. We can use some logical reasoning, but we can also use the calculator to check. So just so you know, for notation-wise, the question is saying, what is the limit as x goes to infinity for this function of 0.8 over x squared? So if I think about that, okay, this time if I was to plug in infinity, right, we don't have an exact number. But what it's really saying here is it's saying something like this, 0.8 over infinity squared. Well, what is infinity squared? It's a humongous number, right? It's not a tangible number, but we know we have this 0.8, which is a tiny number, over infinity squared, which is a huge number. What happens as I have a really tiny number over a huge number? What value do I approach? And what that's going to be is 0. And how can I determine that? Well, again, I can use a calculator or a graphing calculator to make it clear. But when I plug in those values, okay, I will see that the numbers are going to get a tiny and tiny and tiny and tiny and tiny and tinier decimal, approaching 0. I'm going to have you try 3 and 4. Think about what my limit is as I approach infinity. So as I plug in infinities and I get closer and closer to infinity, what happens to that y value? Okay? The next thing we have is our continuity test. So our continuity test is just to see if we're continuous at that point. Okay, so first off, if I'm continuous, it means that we have to actually be defined there, right? If it's undefined and I get an error message, that means there's some gap, some hole, some break in the graph. So I wouldn't be continuous. So that's the first part. Is it actually defined? The second thing is that we have to be approaching the same value from the left and to the right. If we're not, that would mean something like this graph, this second graph. There is a big jump. Okay, and we wouldn't be continuous. So we can see right here, there's a closed circle. So I'm defined at that point, but the graph isn't continuous because I approach different values. Okay, so that's the second scenario. The third thing is that the limit at c has to actually be the value of f of c. And I'll explain that as we do an example. So this first one here, determine whether our function is continuous at 2. And if it is, fantastic. And if it's not, what type of discontinuity is it? So if I plug 2 on in here, I would have 2 times 2 squared minus 3 times 2 minus 1. So is that defined? Do I actually get an answer? Yes, right? 2 squared is 4. 4 times 2 is 8. Minus 6 minus 1. 8 minus 6 is 2. And 2 minus 1 is 1. So I get that it is defined. So therefore, that value will actually exist there. We'll have a closed circle. Now the question is, am I continuous at that point? From the left and to the right, do I both come to reaching that value of 1? So look at the table on the graphing calculator to analyze the left and to the right of 2. Are they approaching the same number? So again, that's where our chart is, right? So if I have my x values and my y values, or f of x, I would have something like this. I would test, for example, 1.8, 1.9, 1.99. And then we have our value of 2. And then I would test, for example, 2.01, 2.1, and maybe 2.2. And I would plug those in to see if we have those same values. If you have the graphing calculator, you can literally look on the graphing calculator to see if we're approaching. But let's test that out. So if I plug that equation into my graphing calculator and then plug these x values in, I get the following. At 1.8, I get 0.08. At 1.9, I get 0.52. I'm just going to jump on over. At 2.1, I get 1.52. At 2.2, I have 2.08. And then at 1.99, and I'm just fixing my table settings so I can get to a smaller value. At 1.99, I'll be at 0.95. And at 2.01, I'll be at 1.05. So let's look at those from the left and from the right. So as I go this way and as I go that way, are we approaching the same value? Yeah, right? I'm both approaching 1. It's not like if I put in with green, it's not like these values are saying 7.08, 6.52, 6.05, and reaching 6, where this side is reaching 1. Both sides are approaching 1, so therefore that's showing that there's not going to be a gap. We're going to be continuous. And last but not least, let's just prove that, right? We can see this limit. What are both sides approaching? Both sides are approaching 1. And we said f of 2 equals 1. So therefore, these two match and they're equal. So therefore, this is continuous. I passed all the tests. Okay, the next one is for you to try. Okay, there are 2 parts to this. You're going to do first test, is it continuous at x equals -3? And then you're going to test to see if it's continuous at x equals 3. If it's not continuous, right, we get some undefined spots, then ask yourself, what type of continuity is it? Discontinuity is it? Is it removable? Is it a jump? Or is it infinite? The next part that we have is the location principle. Okay, and the location principle, again, if you have a graphing calculator, it makes this a lot faster. But our location principle is saying that if f of x is continuous and that we have opposite signs, then we're going to have a 0 between those two values. So what do I mean by that? Let's look at number 7. It's asking us where a 0 might exist, aka where I cross the x-axis between -4 and 4. So I'm going to make a table here for you to see. I'm going to have -4, and it's just talking integers, so I don't need to have any decimals. -4, -3, -2, -1, 0, 1, 2, 3, 4. Okay, so we have all of these values because we're testing from -4 to 4. And we're going to figure out all those y values. If you have your graphing calculator, like I said, you can just pull up the table feature, which makes it a whole lot easier. Okay, so when I do that, at -4, we have -46. At -3, we have -13. At -2, we have 2. At -1, we have 5. At 0, we have 2. At 1, we have -1. At 2, we have 2. At 3, we have 17. And at 4, we have 50. So what is this saying? I'm trying to figure out where my graph will cross the x-axis. Well, I cross the x-axis when I change in signs. So first was negative, then negative, and then we had positive. So right here was a change in signs. Now I'm positive, still positive, but now I'm negative. So in between 0 and 1, I change signs. I'm back to being positive. So between 1 and 2, I change signs. Staying positive and staying positive. And you should stay positive during these notes too. So what does this mean? What this is showing me is that I'm crossing the x-axis 3 different times in this set interval. So when it says determine between which consecutive integers a real zero exists, we have 3 of them, between -3 and -2, between 0 and 1, and between 1 and 2. That is where I would anticipate the graph crossing the x-axis. You try number 8. So this time around, I'll help you set that up. We're going to have a table. And this time we're testing from -3 to +3. So if you have a graphing calculator, those table values will pop right up. Otherwise, you need to plug these x values into the equation to come up with your y values. Then determine where we have changes from negatives to positive. Okay, last but not least, end behavior. This is probably the easiest part of the section, so we'll end on a high note. End behavior is talking about literally what's happening to the ends of the graphs. Okay, so at the left side and the right-hand side, what's happening? Is it going up, up, down, down, etc.? So here's a little chart for you to have understood in terms of notation. If I have a graph where the end behavior in this case is up, up, the way I write that is not to say up, up, but literally to write as x goes to -infinity, right? So as I go to the left, what's happening? Y is going to +infinity. It's going up. And as x goes to +infinity, as I move to the right, what happens to my graph? It too is going to +infinity. It's going up. Okay? So this is the notation on the left-hand side is the notation that you want to have. Now we could have a graph that's going down, down. So what does that mean in terms of notation? It means as x goes to -infinity, y is also going to -infinity. As x goes to +infinity, y goes to -infinity. So notice in terms of notation, guys, this first part is always the same. We talk about what happens first as x goes to -infinity, and then second as x goes to +infinity. What changes is what's happening with f of x and the y. If it's going up, it's +infinity. If it's going down, it's a -infinity. Okay, so let's look at the first example here, and then I'll have you do the second one. If we look here, what's happening on the left-hand side? We are down, and then as we go to the right, it's up. Okay, so it's down and up, but we're not just going to write that. We're going to use our proper notation. So which one of these graphs represents that? It's this guy, down and then up. So what does that mean? What that means is that as x goes to -infinity, we always start on the left-hand side. It's saying f of x is going down or to -infinity as well. Then as we go to the right-hand end, that's x is +infinity. What did we say is happening? We're going up. So that means f of x is going to be +infinity as well. Okay, you try number 10. However, on your set of notes, number 10 is going to look a little differently.